So you can see here that our world isn't very big. I mean, it's large, but for an open world game, it could be much bigger. There are a few problems we run into when trying to make our world bigger. Basically, first using 8-bit versus 16-bit color data for our images. If we use 16-bit images, it would take a little bit longer to process, but we would get more precise values between 0 and 1 for our height values. And that would help a little bit with this pixelation and terracing that you see. And then another problem we run into is that we are limited by the size of our textures that we can use in our shaders. For example, if you're making a mobile game, I don't think you can use textures bigger than 4096 pixels. The simplest solution to increase the size of our world while keeping or increasing the amount of detail in our world was to apply a tiling system to our world generator. This means instead of having each step in our world generator sample a single texture and produce a single texture, we will separate our world map into separate tiles. So instead of producing image textures, we will want our world generator to produce texture 2D arrays. The length of each texture array will be equal to the number of tiles in each row squared. This means that the performance of our world generation system will decrease exponentially with each tile, column, and row pair that we add to our world map. So now that we have this world generation system, I'll show you how we can easily modify it to implement this tiling system. So I think it would make the most sense to start in our world configuration file. We have our tile count, which is the amount of tiles that we will find on any given axis. I made this max tiles variable that I never end up using, but we can use it later on. So let's start by looking at the first step in our world generation algorithm, the landmass generator. So this landmass generator scene I've updated to use our tiling system, and I'll just show you how it works. For our shader uniform variables, you can see that we have our tile count that we will get from our world configuration, and then our current tile so that we can iterate through the tiles at any given point. When we have one tile, this doesn't do much but move around the texture. But if I set the tile count to 2, it zooms in and we can move around which tile we are at. And you can set the tile count to be anything you'd like. So back to the landmass generator shader. We have our tile count and our current tile. And all we've done is add these two lines, tile offset, which converts the current tile to a vector 2 with values between 0 and 1, so we can use it to sample the images correctly. And then we get our actual UV coordinate by dividing our UV coordinates by the tile count and then adding our tile offset value. Before we started setting up this tiling, we just passed our original UV coordinates into these texture function, but now we pass the tiled UV variable into the texture functions. So now let's show the script that lets us save each tile. So here again, everything is the same, but down when we set up the shader, we make sure to set the tile count and current tile shader parameters. Now down in our generate landmass map function, where before we just called viewport.getTexture and then saved the image, now we have to iterate through our tile count, set the current tile in the shader, update our shader, wait for the rendering server.frame post draw so that our texture variable is populated with our image, get the image from the texture, add the image to our images array, and then create a new texture 2D array by calling create from images on the images array. And then you just save it like you would before. So I'll just run the landmass generator so you can see what the result would look like. Alright, so it saved our textures array. I don't know why, but for texture 2D arrays in Godot, when you open them in the inspector, it shows the image really small like this, but you can see that we've split our image up into 4 tiles. In our fault line generator scene, you can see the same thing. We have tile count and current tile, and then we get our tiled UV and pass that into our fault function. And in the script, we do the same thing as the landmass generator. So this will be the same for all steps of the world generator up until you get to the water biomes with unique colors step, where we use the flood fill operation in GD script. Here what we've done is now instead of an image, we have a texture 2D array for lake masks. But now we have this create image data function, which takes all the tiles of each tile map and combines them into a single dictionary with all the combined image data. And then the flood fill operation gets performed on the dictionary of image data as a whole, and then the image data is saved. So here's our create image data function. Here's a new function I've better named set unique colors. Here's the flood fill region function. And then in our save image data function, we make an empty array for our output images. Iterate through the images like you would. And save the correct image data for that image, and then save it as an images array. Moving on to our flood fill altitudes script. We've modified it the same exact way as the last one. These are now texture 2D arrays. We create the image data by combining all the image textures from the array into one giant dictionary with all the image data. Then we calculate the average height for every pixel. Just get our height and width of one image. Then we get the height and width of all the images combined. Track our processed regions. Iterate through the entire dictionary and perform the flood fill collect region function. Accumulate the total height from the image data. Calculate the average height. Set the output image color. Mark the region as processed, and then output the flood filled image data. Flood fill collect region is basically the exact same as before, except now we take a dictionary called image data and we get and set the pixel colors for that dictionary like this. And then we go ahead and save the images like we did before. Actually, this is supposed to say, here we go. And then the next step would be this landmass flat with water biomes. This is essentially the same as we've been doing. Same with the shader. And then for the last step, water biome textures. Again, pretty much the same thing we've been doing. For the shader, nothing special here either. So now, in our main world generator, if I load all the correct scenes with the tiling applied, it should go through each of these steps and generate the image texture arrays. So let's go ahead and run it. Alright, you can see that we have all our texture arrays saved. So now we need to modify our Clipmap system to work with these tiled texture arrays rather than a single image. Alright, so before I get into it, here we have our Clipmap with our tiling applied. And I'm going to show you how to do that soon. So here you can see our tile size. It's how we can control the size of the texture mapping, but it's meant to be kept as the size of our images. So I'll set it to 2048. You can see Our world is definitely a lot bigger now than it was before. You can also see that I've added in a calculation for the normals of the terrain in the shader, which I'm going to show you very soon. So then I thought too, what would happen if I scaled up the clip map itself? You can see that the texture mapping doesn't increase with the clip map scale. So I added in this terrain scale parameter that allows me to scale up the whole terrain if I just go ahead and reduce the amplitude, which makes our world even bigger. Then I just have this normal scale variable, and that's just because I can turn it up really high and see the normals better and make sure they look good. So first, let's look at the shader. So we have our height images array, biome color images. We have our tile size, which is the size of each image in pixels, which will be translated to the world using 1 pixel per meter. Then we have our row size, which is how many tiles on each axis. And we have our terrain scale, normal scale, and amplitude, which you saw earlier. And then I have 2 varying variables, world vertex and world position, so that I can share this data between the vertex and the fragment functions easily. So I have a few functions here, but we'll just start in the vertex function, and through that we'll get to all of these. So first we want to get the positions of each vertex on the clip map in our world space. We do that by multiplying Godot's model matrix times a vector 4 with vertex and 1 as the last element. And this is because you need to multiply the model matrix by a vector 4. And then we just get the X, Y, and Z components. So that gives us our world position where the center is 0 and positive numbers go this way and negative numbers go this way. And then for the purpose of sampling the textures, we want bottom corner of our map to represent 0 rather than the center of our map. Then we get a new correct world position by dividing the world vertex X and Z components by our terrain scale. That way, if I increase the scale of the clip map, it will still sample the correct texture coordinates on the images. And then from there, if I want the world to be bigger, I can increase terrain scale like this. So we do that by taking the world position, adding 0.5 like we did before, so that our collision lines up correctly. And then we add 0.5 times the tile size times the row size to correctly shift the origin of our map to one of the corners. Alright, so then we get our world size, again by multiplying tile size times row size. Get an empty height float variable, set it to 0. And same with our normal, but as a vector 3. And then this is the same as before. It just makes it so the bounds of our map are just black and not repeating the textures for infinity. So now before we sample our height map, we need to create a special tiled texture position. That's because using the texture function on regular images, you would pass a vector 2 as the UV coordinates. But since we're working with sampler 2D arrays, it requires a vector 3 texture position where the X and Y components are the local UV coordinates, and the Z component should be an integer for the layer of the texture array you are on, or in other words, the index of the image in the texture array. That being said, we need a function for getting that vector 3 texture position from our texture position variable. So considering you pass vector 2 of the UV coordinates into this function, you get your tile index by dividing the UV by the tile size, and we use ivec2 instead of vector 2 so that the X and Y components are integers. And we go ahead and clamp the tile index so we don't get any negative numbers or anything. So then we have our tile index in the form of a vector 2. We get it in the form of a single integer by taking the X component, multiplying it by the row size, and then adding the Y component to it. And that essentially turns the 2D array into a one-dimensional array. From there, we need to use our original UV coordinates to get the local UV coordinates for that image. So we have this get local UV function. So let's take a look. All we do here is divide UV by the tile size and use the fract function on it. And what the fract function does is only returns the decimal component of any float that you're working with. So if the float I'm working with is 2.3, it will only return 0.3. So then we just return the local UV. Back to the array texture position, all we do is return a vector 3 with the local UV as the first two components and the layer index as the last one. Back to the vertex function. And I just realized I don't even use this bilinear interpolate function, so sorry if that looked intimidating. Once we have our array texture position, we sample our height map. And then before we finish up, we want to get our normal and set a normal map for the clip map that matches up with our terrain. Let's take a look at this get normal function. We start with an offset float set to 1.0. That's so that down here we can sample each adjacent pixel on our height maps. And then we multiply the value by our normal scale to scale it up or down. HL is left, right, up, down, height left, height right, height up, height down. I also put height center, but I did not need that in my calculation. Set up an empty vector 3 for the normal. For the X component, subtract height left by height right. And then for the Z component, subtract height down by height up. And then you set the Y component to 2.0, and that's just because it should be 2 times your offset. So I guess we could do offset times 2.0. And then you just return the normal value normalized. And that gives you your normals. And then we just do what we did before, multiply our height by our amplitude, and then also by our terrain scale. And then set the normal to our normal value. In the fragment function, have the same kind of setup. Get the texture position, sample the color map, and then I also sample the height map and multiply it by 0.05 so that when we do collisions you can see the collider very easily on the terrain. As for the script, nothing really changed, but we get our terrain scale from our world configuration, and then we have our original terrain snap factor, but we just multiply it by the terrain scale so that everything matches up perfectly. And then you just have to make sure you set the tile size, row size, and then the terrain scale and amplitude. And then I also set the amplitude to be the world configuration amplitude divided by the scale of the clip clipmap object. And that's because if I didn't, when I go to scale up the clipmap, it would scale up on the y-axis as well. So in our world configuration, I set our terrain scale factor to 25 so that you can kind of see what I mean. And then in our game world, I'll scale the clipmap up to 25 so you can see what I mean. Look at that. It's easiest to tell from the speed I'm going because I was going really fast while the world was smaller before, but you can kind of see just how much bigger everything is now. Much more of a realistic terrain scale without too much crazy effort. So now that this works, we want to start working on the tiling for our collisions. So again, like before, we have a scene for our clipmap collision with a collision shape 3D as the scene root, and our script has us assign a player and a template mesh. We can have our plane set up the same way as before by setting the size to 30 and the subdivisions to 29 so that each vertex lines up with the clipmap vertices. So here in the script, everything is the same so far. We get our height texture, our amplitude, and our terrain scale. This is just the size of the images, our row size, and then the terrain snap factor, same kind of thing as the clip map. And then we get an array of our images from the noise texture array. So in the ready function, we set the size of one of the images and the row size so that we can multiply them later. And then we call our function update collision shape to set the actual height values to the vertices of the collision shape. Then in physics process, we snap the collision map to our player just like before, and then update the height values like this. Down to our update collision shape, we set the scale of the collision map to our terrain scale, and then like we did before, we iterate through all the vertices like this, get our global vertex, this time using our terrain scale by multiplying the vertex by the terrain scale and then adding the global position, and then you divide all of that by the terrain scale. And then we call get height, and then set the faces of the shape. So in the get height function, we basically have to calculate the same texture positions like we did in the shader for the clip map. So first we get our texture position with a function called get global texture chords. And this is exactly what we did in the shader. That gives us our texture position. Then, with those global texture coordinates, we need to get our array texture position. We do that by getting our layer index first, the same exact way we do in the shader, just now in GD script. Then we get our local UV. Again, the same exact way we did in the shader, except instead of a fract function, we use this fposmod function, which does the same exact thing as fract. Also, the way that we calculate the local UV is a little bit different because in the shader, the values of the vector2 local UV need to be between 0 and 1 in the shader. But since we use a getPixel function in GD script, if your image has 512 pixels, then your local UV will need to be between 0 and 512 in the form of integers. And then once we have our layer index and our local UV, we construct it the same way as we did in the shader. Now that we have our array texture position, get our layer, get the image on that layer, and then this is where you would sample your height, but I needed to add in our own bilinear interpolation function, and here's why. So if I don't use bilinear interpolation and instead just sample the pixel, then I'm once again ending up with a problem where my collision map doesn't really line up very well with my clip map. And that's because by default, images in the shaders are sampled using a bilinear interpolation filter, as opposed to filter nearest, which is like having no filter applied. The bilinear interpolation smooths the image data with its adjacent vertices, while having it set to filter nearest has no smoothing. Simply sampling the image here is like sampling your image with the nearest filter, and I don't want to use filter nearest for my height and biome color images because I want it to all be smooth. So we just made our own bilinear interpolation function in GD script, where we take the texture position, get the row and column, calculate the difference between the UV x coordinate and the row integer and the y component with the column integer. Then we get the texture array coordinates for all the adjacent vertices to the pixel we're working on, and then we sample the image at each of those adjacent vertices. And then we use the lerp function to perform bilinear interpolation on these height values. So we lerp x1 and x2 with remainder x as the factor, y1 and y2 with remainder x, and then we lerp those two values with remainder y as the factor. And that's bilinear interpolation. So that's pretty much the gist of it. Basically just wanted to show you how we can generate a custom height map for a procedurally generated world, and a few ways that you can customize it and modify it, and then how to make your world terrain much bigger using a tiling system and Godot's 2D texture arrays. The next steps for me, I think, would be compiling a bunch of assets like trees and vegetation, maybe of different kinds depending on the biome, and then use my biome map as well as the other height maps to populate the entire terrain with vegetation and trees. And then we'll want to replace this biome colors map with actual high detail terrain textures. And then I'd probably want to improve the normal calculation on the clip map. The next thing I'm going to try in another video probably is adding in an actual ocean water plane and maybe some basic swimming. And then I'm going to try to add a bunch of water biome planes around the world so that hopefully you can swim and drown in any of the water biomes that we created. If you would like to support this work and help me make more of it, feel free to buy me a coffee on ko-fi.com. And if you wanted to support me further, I now have a Patreon where I will be releasing videos early before they appear on YouTube. So that's pretty much it. I hope you liked this and I hope it helped. Thanks for watching.